In this module, we're going to be looking at survival data. Specifically, we're going to be using the Kaplan Meier analysis. It can be accessed either in the left menu or under the drop-down menu in the Select Type of Analysis box under Kaplan Meier. Right now, we'll be accessing it through the left menu by clicking Kaplan Meier. You then get to the screen where you can select a dataset. Right now we're going to be using the neuroblastoma dataset with 88 samples. There are, however, more datasets that have survival data associated with them. For now, we're just going to keep the dataset we already had selected by closing the selection screen. We're going to be looking at a single gene, so separate the groups based on a single gene. Click Next. We're going to look at MIC-N. Just type MIC-N in the left box and select the corresponding probe. And we're going to look at overall data. And then you can click Next.
So what we are now presented with is a Kaplan Meier plot, which is this typical plot here on the left. So there's a few things that we need to understand in order to read a Kaplan Meier plot. So what is a Kaplan Meier analysis? How this works is that you divide patients or divide samples into a certain number of groups. In this case, we divided them into two groups, comparing a low expressing group to a high expressing group. And we are then going to compare the groups based on the survival of patients in these groups. In this case, we are looking at overall survival. And you can also see here in the left menu that there is an option to look at relapse-free survival as well. For this data set, you might also find event-free survival or other options depending on what type of data is available for that data set. So how we look at this is that we start at time point 0, where 100% of patients are still alive at that time point, and then we look at how these groups survive over time. So for each step down, it is an event or percentage of events that are happening in this subgroup of patients, and the remaining percentage of patients that are still alive after a certain amount of time. So each step down in this case represents one patient succumbing to the disease. If you, in certain cases, have a larger step down in over one time point, as you see here in the low expressing group, you can see a larger step down. That would imply that more than one event is happening or more than one patient is succumbing to the disease. What you can also see is that each step down here, which represents one event, is quite large compared to the steps down that you're seeing in the low expressing group. And that is due to the fact that each patient that is succumbing to the disease represents a much larger proportion of 12 patients than the one patient that's succumbing to the disease, representing a proportion of the 76. So that is how you can compare what each step represents in these types of graphs. And what you can also see is that over time, for instance, between 24 and 48 months, the high expressing MIC-N group has approximately between 5 and 10% of patients surviving, whereas at the same time point in the low expressing group, you have approximately 75% of patients surviving. So there is quite a difference there. You also notice on the curves themselves that you have these little ticks, and these ticks represent censored events. So what that means is that it doesn't imply that a patient has succumbed to the disease. It means that the follow-up information for that given patient has finished at that time point. So as of just after 72 months, there is no longer follow-up information available for the high expressing patient group. You will also see that you do get statistics associated with this curve to tell you how significant it is. And we provide both a raw p-value as well as something called the Banff p-value, which is the Banff-Ferroni p-value, which is corrected for multiple testing. Now, why is it that we want to correct for multiple testing in this case? And that is due to the fact that in order to represent the data in this chart the way we have, we've performed something called the KaplanScan approach. Now, in order to explain that, we're going to look at this expression graph on the right. And just as we discussed in the single gene view, we're going to rank all the patients from the lowest expressing to the highest expressing based on MIC-N expression in this case. And what we've now done is, for the KaplanScan approach, we divide the patients into as many two different group comparisons as possible based on low versus high. So what happens here is you start with in theory, one patient in the low group and all the rest in the high, and then you move to two patients in the low group and the remaining in the high, and you make every comparison all the way up to the other end where you only have one patient in the high group compared to all the rest in the low. And underneath this, you will then see that we have plotted the negative log of the p-value. So the most significant cutoff is represented here as the highest peak, and that is where we have chosen to make the cutoff for this plot. Now, through that description, you can understand that we had to compare many different analyses, many different group comparisons in order to choose the most significant p-value. And therefore, we must correct this p-value for multiple testing, which is why when you do such approaches as the scan approach, you need to report the Bonferroni corrected p-value and not the raw p-value. So that was how we use the KaplanScan approach. Now, however, there are multiple ways that we can divide patients into different groups. So the KaplanScan is the one that's set by default. However, if you scroll down to the adjustable settings, you can see that you do have multiple options of different types of cutoffs that you can select. So you can split the groups or split the patients into groups based on the median expression, which divides the patients equally into two differently sized groups. You can split the groups based on average expression, or you can compare the highest expressing quartile versus all the rest, or the lowest expressing quartile versus all of the rest. So why don't we have a look at how the median expression looks? So we select median, and then we're going to redraw the graph. And here you can see that we have two equally sized groups. So we've compared a lower 44 patients to the higher expressing 44 patients. And here again on the expression graph, you can see exactly where they've split them into the two groups. Here you can see that we only supply one p-value, which is the raw p-value again. And this is because we've chosen only one cutoff and we're performing only one test at this time. So you do not need to correct for multiple testing. So again, as I selected the median expression, you can also select, for instance, the last quartile or first quartile versus the rest of the patients. So we'll select the last quartile. And again, we're going to redraw the graph. And here you can see that by selecting the last quartile, you're selecting the highest expressing group and comparing it to the rest of the patients. And again, you can see that only one p-value is supplied, and that is because we are only performing one statistical test or one group comparison. There is also another method of defining groups that we can have a look at. And in order to do so, we're going to go back to the main page.
We are going to do the same thing as before. We go to Kaplan Meier, we keep the same data set, we go to a single gene separation and click Next. Then here we can again select MIC-N and go for the overall type of survival. But this time we're not going to use the scan, but we're going to use the curtain as the cutoff mode, and we can click Next.
How the curtain test works is it divides the patients again into two groups. However, it starts in the middle at the median expressing patient or at the median expression cutoff, and then it moves outwards, eliminating one patient at a time from each side until you have the lower expressing group compared to the higher expressing group that creates the largest difference or most significant p-value. Again, because we move out one patient at a time in each direction, we are now performing multiple tests, and you therefore require a Bonferroni corrected p-value for multiple testing. So that's how a curtain Kaplan approach works in this instance. And you can also select, for another example, for instance, the first versus last quartile, which is similar to the curtain. However, you're only selecting the first quarter or lowest expressing patients versus the highest quarter of expressing patients. So we can click on that and we can have a view. Now here, again, because we're not performing multiple tests, we're predefining the groups that we're going to compare. We are only supplied again with one individual p-value that is representative of the lowest quarter, 22 patients, versus the highest quarter of 22 patients. So now we've shown you a few different ways that you can use gene expression to divide patients into different groups to compare. And in this case, we've looked at MIC-N expression and accessed the Kaplan curves via the Kaplan Meier menus on the main page or the drop-down menu on the main page. But we can also show you that there is an option if you are in single gene view or view a single gene, as we have discussed in a previous module, if there is survival data associated with that data set, you can also access that data from the View a Gene page here on the left. So if you were to click on that, you will then be brought to the MIC-N overall survival curve, which is defaulted to the Kaplan Meier scan approach, which we discussed earlier. A few other options that we can discuss is that you can choose to set your own colors, for instance, and other adjustable settings that we will discuss in a later module regarding adapting R2. Also, if you have defined groups of patients based on gene expression and split them up into high-low based on this Kaplan scan approach, as we have done here for MIC-N, you can also store these groups as tracks for later use, or you can store them for temporary use. So if you return to the Kaplan plot, that this result will be stored temporarily until you make a new plot. Discussing how to store tracks will be discussed in a different module where we will set a link up to here. So we have shown you a few examples of how you can use the different methods to define optimal cutoffs in different ways using gene expression to define groups for your Kaplan Meier analyses. However, there are ways that you can define your specific cutoff with regards to gene expression. So under adjustable settings, for instance, you can select a specific cutoff, of which you can see all the possible cutoffs here and their associated both raw and Bonferroni p-values. Or for instance, you can select on this ranked expression graph itself, you can select a specific point for the cutoff to happen, or select a specific point associated with a specific p-value. So for instance, if I click here, it will then redraw the graph with this new specific cutoff that you were able to specify. So far, we've been looking at using gene expression to divide patients into different groups and look at survival data. However, there are multiple ways of dividing patients into groups.
We go back to the main page. We go again to the Kaplan Meier. This time, we're going to select for a categorical track as a separation and click Next. We can set the type of survival again to overall, and the track this time we can choose INSS and click Next.
Here you can then see that the patients are grouped into 5 different groups, stages 1 through 4, and then stage 4S patients. And because these are static groups and predefined, we are only performing one test, and therefore one p-value is provided for this comparison. You can also scroll down to the adjustable settings where you can select using different tracks, so you can compare different groups of patients that are predefined. So for instance, if we want to look at MIC-N amplified versus non-amplified tumors, we can select that 2 category group. And again here, you are supplied with one individual p-value comparing the amplified tumors versus the non-amplified tumors. So in this example, we've looked at using tracks as categories to separate groups, in which case the subgroups are predefined by the track itself. It is also possible to look at tracks that are numerical and define cutoffs within a track.
So for instance, if we go back to the main page and go to Kaplan Meier again, we can this time select for a numerical track. And also we're going to change the data set to one with 498 samples. Here we can select for the one that is normalized with RPM and select, then click Next. And in the next screen we are then required to choose a track that contains numerical values to separate on. In this case we can go for age at diagnosis. And for type of survival we can again choose overall, so that it matches with what we've been looking at so far. We can click Next.
So what you see here is a graph that looks slightly different than what we've seen before, and this is because this data set consists of many more patients. You can see here it consists of 498 patients. And this is now looking at, instead of gene expression values or a track as in a category or subgroup of patients, we are now looking at all patients ranked based on their age at diagnosis when they were diagnosed with the disease. And you can see here that using this KaplanScan approach, the same way that we applied it to gene expression, we've applied it to a numerical track, and we have defined the optimal cutoff being at exactly 582 days, which, interestingly, knowing biology about neuroblastoma, coincides with approximately 18 months of age at diagnosis, which is used as one of the clinical criteria for defining high-risk patients. So if you are above 18 months of diagnosis, you are considered a high-risk patient, which this approach then exemplifies. So far, we've looked at examples of using both individual genes or individual tracks in order to perform these Kaplan analyses or survival analyses. But there are also options to look at multiple genes at once to find which genes are the most significantly associated with overall survival.
For this, we're going to go back to the main page, go to Kaplan Meier, separate this time on multiple genes, and click Next. We're going to keep the cutoff mode on Scan, meaning that it will choose the optimal p-value for each gene. There are a number of gene filters you could set, but if we leave this as it is now, without any gene filters on, it will scan all the genes present in your dataset and provide you with the list of genes that are most significant associated with survival. And we'll leave the type of survival as overall, and we'll leave the statistics as they are as well, and we can click Next.
So what we were provided with here is a list of all genes that are significantly associated with overall survival. These genes are then ranked according to their adjusted p-value or significance of association to survival. And under more information, you can also see the number of patients that are defined in the first group, or the low expressing group, the average expression of your gene at that cutoff, as well as whether high or low expression of the gene is associated with a poor prognosis. And you're also given the raw p-value. So for each of these analyses, you can also click on the individual gene, which will then bring you to the associated Kaplan Meier curve for this gene and the specific optimal p-value cutoff, as we've discussed before. So if we return to the gene list, you can see on the right-hand side that you do have also options that you can perform further downstream analyses on these genes that are associated with overall survival, such as performing a gene ontology analysis, or you can even store your list as a gene category, which you can then use to perform analyses downstream in the R2 platform.